All right, so let's talk about these review solutions. So the first question is we have oppositely charged glass and plastic rods hanging by threads. An object attracts the glass rod. And then if this object is then held near the plastic rod, it will. So there's two things that could be going on here. The object attracts the glass rod. So we haven't actually been told that the object is charged or how it's charged. So if this object attracts the glass rod, one of two things is going on. One is that we know the glass rod is charged, so if the object is neutral, if it's uncharged, then it will feel a polarization force, and that would be an attractive force. So we know that A has to be true. So we have an uncharged object in the vicinity of what we know to be a charged glass rod, then there would be a polarization force. The other option is that the object is charged. Since it attracts the glass rod, and we know that like charges repel and opposite charges attract, we know that this object has the opposite charge. We would know that the object has an opposite charge to the glass rod. So if we take the thing that has the opposite charge to the glass rod and move it near the plastic rod, which is charged oppositely from the glass rod, that would be two like charges next to each other, and that would mean that it repelled. So if it's charged, then it would repel the plastic rod. If the object is neutral, then it would attract the glass rod. And without more information, we can't tell whether they're both, which one is right. So the correct answer there is D. So the next two questions are vector questions. So they have drawing arrows in the direction of electric fields and electric forces. So the way that I like to do this is to take one charge at a time. So in question 2, we have two source charges, a positive one and a negative one. So let's pretend like the positive one is not there and figure out what the electric field would be at this dot. We know that electric field points away from positive charges and toward negative charges. So at this dot, there should be an electric field, and I'll label it E minus, that points toward the negative charge. The next one is get rid of that charge, and now let's just figure out what would be going on here. So at this dot, due to the presence of the positive charge, electric field points away from positive charges. So we expect this to be something that points to the right. And now we have to kind of think about the length of this vector. So I'm going to go ahead and draw the length of this vector like that, as being short compared to the other one. I drew this as being short because this distance here is a big distance compared to that distance. So I expect that the electric field and any electric forces as well would be stronger for the charge that's close and weaker for the charge that is far away. So the vector sum of this is we're going a little bit to the right and a lot to the left. So our net vector should point to the left. If you want to if you can just see that we're going kind of more to the left than to the right, that's great. You don't need to do any more work. If you want to add these head to tail, then you could do imagine kind of rearranging these vectors so that the head of the first stacks up with the tail of the second. So that would be sort of rewriting that as we're going to go to the left, E minus, and then I want to just imagine picking this one up and putting it so that the tail of the second one overlaps on the head of the first. And here I have to kind of offset them a little bit because otherwise that would be hard to visualize. So we're going to the left a lot, to the right a little, and our net resultant vector would go from the beginning of the first to the end of the last, so it would point to the left. Either way, you get the same answer. The last problem on this page is very similar to the second problem, only rather than being a two-dimensional problem, it's a three-dimensional problem. And I'm also asking you both for the force. We'll do the force on this one and the field on this one. And for the force, we'll specifically be looking at a negative charge at the location of the dot. So electric field at the dot. Electric field points away from positive charges, so let's get rid of this one. At the location of the dot, I know that it should point away from the positive charge, so I'm going to draw an arrow like that. That's the electric field pointing away from the positive charge. Points toward a negative charge, so I'll go ahead and draw an arrow pointing toward the negative charge, and I'll label that as the E minus vector. And the net electric field will be the vector sum of these two. Again, if you can just kind of visually see that both of these are going to the right, and this one here on the top is going up a little bit, and this one here on the bottom is going down a little bit, and they will cancel each other out, then that is just fine to kind of be looking at that and recognize that the net E vector will point to the right. If you want to go ahead and add these head to tail, then you could imagine picking up this vector and just moving it. So we're not going to change its length. We're not going to change its angle. We're just going to change its location. So if I picked up the E minus vector, picked it up from there, and moved it to there without changing its angle or its length, then I can have the E plus vector and the E minus vector adding head to tail. Right, we're going tail, head, and then the net vector would start at the beginning of the first and go to the end of the last. So D is the answer for the electric field, the first part. And now for the second part, we're just going to take this same configuration, only now imagine that there's a negative charge. So in equation form, we have that the forces, force always points in the same direction as the electric field for positive charges. It always points in the opposite direction for negative charges. So since we have a negative charge here, I know that whatever the electric field was doing, the force will be doing the opposite. So it's as simple as recognizing that, since we already did it for the electric field, that I know it's got to point to the left in the end. So that would be a completely fine and sufficient way to think through this. If that's not enough and you want to double check your work or just kind of think about it in a different way, you can imagine just putting a negative charge right there and do the same thing that we did for the electric field. So we'll get rid of that. And now we have a negative charge and a positive charge. They should be attracted to each other. So I would expect to feel that this negative charge here should feel a force that is pulling it toward the positive charge. So if I label that as being F plus, points toward the plus. Now if I get rid of the negative charge, or get rid of this positive charge and just look at the negative charge, now I have a negative next to a negative. Those should repel each other. So this here will feel a repelling force. And I'll label that F minus, pointing away from the negative charge. So same thing here. We have this one that goes to the left and up, this one that goes to the left, this one here that goes to the left and down, and the sum of them will be a vector that points to the left.